Today we're going to take a look at factoring. We've been factoring some items already. We're going to go a little bit further today. Some of the items that we're going to look at today might feel like, didn't we kind of already do that? And the answer is on some of them, yes. So there's some of these all sort of mixed together in what we're going to look at. I think I've referenced this phrase before, but don't believe that I've actually physically defined it and written it down. So we're going to start with talking about what a greatest common factor is. So a greatest common factor is the largest factor of two or more, no, I didn't say that right. It actually is written right. The largest factor two or more terms have in common. Okay, so factor means it divides it evenly. So if you want to call it the greatest common divisor, it's the same thing. So divisor and factor, same word. This is 38. 37 is the quiz that you just took. Yep, so skip a page for 37. This is page 38. All right, so sometimes this is just a number. Could be that two terms have only something in common in terms of their numerical value. It could be just a variable or a variable to a power. It could be a combination of both of those things. Or it actually could be the number one. They don't really have anything in common, but they have an understood one, of course, in common. So you have lots of options that can happen when we're looking for greatest common factors. Now, the ones that we're going to be dealing with, we're not going to see the case where they don't have anything in common. That's not what we're going to see happen for the most part. And in fact, when it does happen, you're not even going to realize it's happening because you're just going to say they don't have anything in common and you're not going to do anything. So there are cases where that's going to happen, but you're not going to think of it that way. So let's take a look at finding the greatest common factor of a few examples. Okay, so taking a look at example number 1, we have 9n cubed and 15n squared. So we're going to start with the numbers, 9 and 15. What do 9 and 15 both divide by? The biggest thing. 3. So I'm going to write a 3 down. That's going to be part of my greatest common factor. Here, I'll label it. This is a GCF. It's going to have a 3 in it. And then look at the n cubed and the n squared. Obviously, they both have an n. How many n's do they each have in common? 2 of them, or squared of them if you prefer. So there's n squared. So 3n squared would be the greatest common factor. Okay, that's all we're asked to find here. We're not asked to do anything with it, just identify it. Let's try the next one. I said it was 2 or more, right? So this one has 3 numbers, or 3 terms with it. 14, 7, and 6. What's the biggest thing that they have in common with the number parts? What is it? They don't have anything but 1, right? If I looked at 7 and 14, they'd have a 7, right? If I looked at the 14 and the 6, they'd have a 2. But 7 and 6 don't have anything in common, so they don't have any numbers in common, except for we could say the number 1 if you wanted to sort of just verify to yourself that you had sort of checked that part of it. So you can either leave it sort of blank for that part, or you can write the number 1. Now let's look at the variables. This is x squared, x to the 4th, and x cubed. How many x's do they have in common? 2. The first one has 2, the second one has 4, the third one has 3. So 2 is the most that they all have in common. So it's either x squared, or you could say 1x squared, if you'd like. All right, so saved the best one for last, obviously. Messiest anyway. I have a 20 and a 5. What do they have in common? A 5. So sometimes they'll actually have one of the values themselves as the common factor. That can happen. And then we're just going to go sort of in order of the way they're listed, or you can go alphabetical, or it doesn't matter. There's v to the 5th here. And what do you see in the second one? There's no v's, right? So there's nothing that have in common in terms of the v's. How about the u here? How many u's? 2 of them, right? So it's u squared. And then we have the w's. So how many w's do they have in common? all three of them. So I have 5u squared w cubed. All right, so the note at the bottom of the page says what we're going to do with them. I mean, all I said here is we're just identifying them for now, right? What are we going to do with them? Well, these greatest common factors will help us to factor binomials and eventually trinomials as well. But for right now, just binomials. We're looking at two terms, kind of like on number 1 and number 3 here, and we're saying what do they have in common? And I'm going to factor it out in front. So let me show you an example of that with number 4. Number 4 is a pretty straightforward one. I'm going to compare the two terms. Remember, terms are separated with addition or subtraction. So I do have two of them, 14 and 7w. What do they have in common? They have the 7, right? Okay, so factoring means pulling out what they have in common, which is essentially dividing. What is 14 divided by 7? 2. And what is, and then there's a plus, what is 7w divided by 7? W. Now, notice this is different than the last lessons where we had equations. They were set equal to 0 and we kept going, right? There's no equal zeros here. So resist the urge to put equal 0 and find solutions. We don't have that. We're stopping right there. Okay? So there's no solutions in that sense in this lesson. We'd stop here. How about number 5? What do they have in common? They have an A in common. So if I factor out an A from 9a, what do I have left? 9. The sign will stay the same. And if I factor out an A from 13a cubed, what we'll have? 13a squared. Now how could I check to make sure I did it right? Yeah, I could do the distributive property and multiply it back out, right? And if I did it right, then it will equal where I began. Very good. All right, so again, saving the best until last on this particular slide. Number 6 is rather messy. Start with the numbers again. So 3 and 18, what do they have in common? A 3. And then I have u to the 4th, and I have u squared. So what do they have in common? U squared. And then I have w to the 9th and w to the 6th. Does w to the 6th. And then while the second one has an x cubed, the first one doesn't. So there's nothing else to pull out, right? Okay, so this one's the hardest to pull things out of. So let's compare it piece by piece. Clearly the 3 got pulled out completely. How many u's do I have left? I have 2 of them, so this is u squared. And then how many w's do I have left? 3 of them, so it's w cubed. And then I've got my sign, my positive sign. Okay. And then on the next one, we're doing the same thing. We're using 18 as our starting point. So if I have 18 and I pulled out a 3, and we're pulling out its division, what would that leave me with? It would leave me with a 6. The u squared, I pulled out a u squared, so that's just gone, right? It divides to 1 is what really happens. And then the w to the 6th, already also gone, right? It's because it's a w to the 6th. But I have still the x to the 3rd, x cubed there. So this is kind of a mess, but I'll just rewrite it for clarity. 3u squared w to the 6th times u squared w cubed plus 6x cubed. And if you've done all of the factoring out you could do, what it means is that when you look at this part in parentheses, the two terms don't have anything else in common that match. There's no more matching pieces. They're not both even still, or they aren't both multiples of 5, or they don't both have an x in them, that kind of stuff, right? They have to be, we call it relatively prime. They have to have nothing else in common to one another, all right? Let's try one more. And these are a little different now. That's why I'm on a different slide. please don't multiply them out. Distributing will not help you here. Okay? There are actually two terms. There's this term separated with addition from this term. Is everybody okay with that so far? I know the terms themselves have got addition and subtraction in them, but we do have two terms separated with addition. Now, if I look at the first one and I compare it to the second one, what factor do they have in common? They have y minus 2 in common. Does everybody see that? That's distinctly different looking than the ones we've done before, but they do have a y minus 2 in common. So what I'm going to do is I'm going to factor the y minus 2 out in front. We've already looked at this a little bit in another example 2 or 3 days ago. If I take the y minus 2 out of this first entire term, what am I going to be left with? 3y squared. Again, the sign has to match, so there's a plus sign here. And if I take that y minus 2 out of the entire second term, what's left? A 2. Good job. And this would actually be my answer in factored form. Okay, so I've got a typo on this one I can see already. This is what happens when you're doing it at 4 in the morning. Okay, there's a 7 there, pretend. You can fix it real quick, right? No problem. Okay, without me marking things up, what do the two terms have in common? Right, they both have a 2u minus 7 after I fixed it, right? So if I take a 2u minus 7 out of the first term, what am I left with? 4u and a plus sign. And if I take a 2u minus 7 out of the second term, what am I left with? I'm left with 1. It looks like it's nothing. I've taken everything out. But remember, when I'm taking things out, I'm dividing. So when you divide something by itself, you get 1. Another way to think about it, if it helps you, is that there is, without seeing it, of course, an understood 1 right here in front, right? Yeah, so that coefficient there of 1 is what's left. So I end up with 2u minus 7 times 4u plus 1. All right. Going just kind of one step further, one level beyond, we're going to talk about factoring by grouping. Factoring by grouping, we've actually already done. I just didn't call it that when we did it. It is the process of grouping terms together using the greatest common factor to break apart 4 or more terms into groups of 2, resulting in identical binomial terms to allow the complete factoring. I showed you this method, at least a portion of this method, when we did the AC method of factoring trinomials. That's where you will have seen it with me anyway. but it works more broadly than just right there. So we're gonna start with an example where we see it working more broadly, and then we'll do it again to see how that AC method is playing into that patterning. Okay, can I switch my slide? Are we good? Okay. So example number 9 is w cubed plus 3w squared plus 6w plus 18. Now in theory you might have to shuffle some terms around, but in reality most of the time the way that they're already positioned will work. So if I pair them up just one after the other, I make two sets of two groups of 2. I do the same thing that I was doing way back like over here, where I said what does they have in common? Okay? So the first part that's underlined in red, w cubed plus 3w squared, what do they have in common? A w squared, right? We're just looking at these two terms. They have w squared in common. And if I take out a w squared from the w cubed plus 3w squared, what will remain? W plus 3. The addition sign, or if there had been a subtraction sign, would come down. And we repeat the process with the second set of 2 terms. 6w and 18. What do they have in common? A 6, right. And if I take out a 6, what will remain? W plus 3. Now, pause for a second. I want you to realize we are now at the same position that 7 and 8 were at when we started, right? Okay, so these examples 9 and 10 are really just one additional step from what we already did. So now from here, if I can compare this term and this term, what do they have in common? The w plus 3, you got it. And if I take a w plus 3, excuse me, out of the first box, the first term, what do I have left? W squared, and out of the second, I have plus 6. Nope. Good question. It does not matter because remember we're talking about multiplication, which is commutative. 5 times 2 is 2 times 5, so it doesn't make any difference at all. Okay, and number 10 is actually one that we could do with trial and error, and if you want to do with trial and error, that's fine. But I wanted to show you that when we talked about the AC method, this is what we were doing. We were doing factoring by grouping. So what we did is we broke the 12 down, and we said, what 2 numbers, in this case everything's addition, what 2 numbers multiply to 12 and add to 7? It would be 3x and 4x. And if you put 4x and 3x, totally fine. Your work looks a little bit different in the middle, you'll get the same answer at the end. Now I have 4 terms. So the 4-term process is called factoring by grouping. So I took 2 terms at a time. And in the first set I said x squared and 3x. What do they have in common? X. And if I take out the x, I get x plus 3. And then I've got the addition sign. 4x and 12. What do they have in common? 4. And if I take out the 4, what do I have? X plus 3. Now, here's something important to notice. If you got different terms inside those parentheses, like one's at x plus 3 and one's at x plus 2, you've got an error somewhere. Maybe you broke down the middle part wrong. Maybe it's not 3x and 4x. Or maybe you did your division and your factoring wrong, okay? But there's a mistake somewhere. If you're doing the process and you're not getting those terms to match right here like this, you've got a mistake somewhere. So, what do these have in common? X plus 3. And if I take out the x plus 3 from each one of them, what will remain? X plus 4. Okay, any questions on that? Excellent.